Hi. So we now come to the last sub-module of the seventh module, and today I'm going to talk about bitmap indexing, bitmap indexes, which are very popular in data warehousing, and it comes under a very broad topic of indexing the data warehouse. So although I'm not going to talk too much about the other kinds of indexes, I'm going to spend time on bitmap indexes because other kinds of indexes you might have already gone through them in a course on databases, so I'm skipping that, and whenever there is a reference I'll give you a little overview of that. But here I'm going to talk about bitmap indexes, which are multidimensional indexes, and they suit the multidimensional queries nicely, and that's why they are used extensively in data warehousing. So topics are bitmap indexes, advantages over hash and tree based indexing structures. So hash and tree based indexing structures are common in databases, so those are used as it is in data warehousing as well. And then how to carry out and or operations. I mean, how these bitmap indexes support these operations, which are very common in data warehousing. And then multidimensional queries, like how we can answer multidimensional queries using bitmap indexes. So these are the topics that I've outlined for bitmap indexes. So bitmap index is a promising indexing approach for processing complex ad hoc queries in a read mostly environment. So read mostly, so as we know that data warehouse is a read mostly environment, so this is a very promising technique or indexing technique for such environments. So indexing structures, so just an overview. Indexes are data structures that are used to retrieve data efficiently from databases. So this we all know, and it has a very good analogy for this is the index at the end of a book, so through which you can retrieve whatever information or whatever topics you want to read about quickly in a book. And indexes reduce search space before going to the primary source data, and indexes take much less space as compared to the data that they're indexing, and they're extensively used in OLTP systems, and the common indexing structures are tree based and hash based indexing structures. So in tree based you have B trees, B plus trees, and then these are one dimensional indexes, and then you have R trees, KT trees, quad trees, right? And similar multi-dimensional data structures, tree-based data structures, and then we have hash-based, so where you have linear hashing and extensible hashing, right? So all these are like, so here we have static and dynamic indexing structures as far as hash-based indexing is concerned, and these indexes are designed in such a way that they retrieve a small fraction of records satisfying a given selection condition. So they, what I'm trying to say here is that they are not suitable for large amounts of when you want to retrieve large amounts of data from a database. So in the next slide I'm going to talk about that. So they are not suitable for queries that require millions of records to be answered. So for example, total sales over a period of 3 years, right? So basically we call such queries as queries with large footprints. So they require lots and lots of records to be retrieved before we can answer them, and compare it with an OLTP query like find the balance in account number 100, right? So those are very narrow queries, and here the queries are very broad in the sense that they have large footprints. And in such cases it is better to bypass the index that you have and do a complete table scan, because you are requiring most of the records that are there in the table. And these are one-dimensional indexes not suitable for multi-dimensional queries in a database environment, data warehouse environment. So for data warehousing environments, we need indexing structures that satisfies the following criteria. So they are able to efficiently retrieve large number of records from a table efficiently, and handles multidimensional queries with conjunctive selections like AND or conditions, facilitate joins and aggregations, and are space efficient. So so keep a tag on all these points that I'm mentioning here, and as we go along this lecture, you will find that bitmap indexes satisfy all these conditions. So it was proposed by Patrick O'Neill in '87, and these are suitable for low cardinality attributes, and adaptation to high cardinality attributes also possible and available. So I'll be talking about that as well. And these bitmap indexes are highly amenable to compression and encoding, making them much compact than the corresponding hash or tree-based indexing structures. So I'm going to talk about compression and encoding also in the next lecture, right? And bitmap manipulations using bitwise operators like excuse me. Bitmap manipulations using bitwise operators like AND, OR, XOR, NOT are very efficiently supported by the hardware. So there is hardware support for these operations, so that also helps in improving the performance using bitmap indexes. So why bitmap indexes? Because most of the other multidimensional indexes like multidimensional indexing structures suffer from what is called as the curse of dimensionality. So for example, R trees, KD trees, quad trees, they all suffer from the curse of dimensionality problem, and so as a result they don't scale to large number of dimensions, say greater than 10, and are efficient only if all dimensions are queried. All available dimensions are queried. So these are the limitations. So that's why bitmap indexes we say are efficient for multidimensional queries, and response time scales linearly in the actual number of dimensions in the query. So if there are more queries, more dimensions in a query, then it will scale only linearly. So what is a bitmap index? So to understand this, let us take a simple example. Say you have data values, say of an attribute in a table. So 0, 1, 5, 3, 1, 2, 0, 4, 1. And so what we do is we create a bitmap called B0, right? Then we create a bitmap B1, B2, B3, B4, B5, right? So there are 6 values. So 6 bitmaps or bit vectors, as we call them, are created, and the collection of bit vectors is a bitmap. So each one of them is a bit vector. So we call them bit vectors. So 0 and up to bit vector 5, and these are collectively called as a bitmap index. Okay, so bitmap indexes, as you can see, is nothing but a matrix. So you can see B0, what are the entries in B0? So the first entry is 0, so that is why there is a 1 here, and wherever there is a 1, there is a 0, I'll put a 1. B1, so wherever there is a 1, I'll put a 1. So here it is 1, so there are 3 1s in this. So, and 2, wherever I encounter 2, so 2 is encountered only once, and so on. So this is how I put it. So it tells me, so B0 tells me that the first record in this attribute, first record in this table has a value 0 for this attribute, right? So compact, so they are compact, 1 bit per distinct value per object, and easy to build. So and it can be built in order of n time versus order of n log n for trees, and they are efficient for queries. So all these points I'll discuss in the next few slides. So a relation, so I'll continue with some examples. A relation R with cardinality 12, right? So there are there are 12 records or 12 tuples in this record, and there is an attribute A on which I've taken a projection, and the values are shown here. So so the values are shown here for the projection, and now again, so there are 9 distinct values, so I have 9 bit vectors. So B0 tells me that this particular record has 1, and so on. So this is called as a value list index, and so this is a more appropriate or more commonly used representation. So you can see, so there will be 9 bit vectors or 9 bitmaps, each corresponding to a distinct value of A, and in each bitmap the position of 1 gives the record number. So if you look at 2 right here, if you look at 2, so it tells me that the 2nd, 4th, 6th and 7th records are have value 2 in this particular attribute on which I have created a bitmap index. Now let me just take you through one or two examples and illustrate how and or operations can be carried out to answer multidimensional queries. So this example has been taken from the database systems book by Garcia Molina, right? And it is about who buys gold jewelry, and the database that is available is that of age and salary, right? Assuming that age and salary are the only relevant factors, and there are 12 customers which I have listed in this table, right? So what I'm doing is I look at age and find out all the distinct values for age. Similarly, I look at salary and look at all the distinct values, and I find that the distinct values for age are like that, are 25, 30 and so on, and similarly for salary. And then I create a bitmap index on age and also create a bitmap index on salary, and this is how it looks like. So you can see that if I look at the first bit vector here, so it is 25, so 25 age, so you can see 25 age is this and 25 age is this, so 12, 11, 10, 9th, so first and 9th records have age 25, right? And similarly other age values, and similarly for the salary values. So this is what I have. Now suppose we want to find the jewelry buyers having age 50 and salary 120. So suppose this is my query, right? So to find this, I will take the bit vector corresponding to age 50, and also I'll take the bit vector corresponding to salary 120 and do an AND. So when I do an AND operation, so it tells me that the fifth entry, fifth record is this, so first, second, third, fourth, fifth, so that is the record that will be retrieved, right? So there is only one record that satisfies this condition, and it is very efficiently picked from the database. Now there are other kinds of queries. So this is an example of point queries or equality queries where age is equal to 50 and salary is equal to 120. So bitmap indexes are also suitable for range queries. Now if you recall hash and tree based indexing structures, so in hash, so they are good for equality queries, and tree are supposed to be good for range queries, whereas bitmap indexes are equally good for both equality and range queries. So here is an example of a range query. So what I'm saying is find the jewelry buyers with an age in the range of 45 to 55 and salary in the range of 100 to 200. So what I need to do is I need to look at all the values that are there between 45 and 55, and I find that there are only two such values, 45 and 50, right? And I'm looking for a salary range of 100 to 200, so I find that there are four such values, 100, 110, 120 and 140. So when I take age, so I have got two bit vectors now. So what I do is age could be anything between 45 and 50, so that is why we have to perform an OR operation. So when I perform the OR operation, so this tells me that all the records which are in this range, right, 45 to 50. Similarly, the bit vector, when I do an OR of all these four values, right, so I get this bit vector which represents all the customers with salary between 100 and 200. And finally, if I were to combine these two using an AND, this will give me the answer for the query. So you can see that only the fourth and fifth records qualify, and those are marked in red ink in the slide. So those are the fourth and fifth. So no other customer would satisfy this condition. So this is an example of a range query, and it works equally. Bitmap indexes work equally well for both equality and range queries. And points to note in this are that bitmap index tell us only about the position of records that qualify to be included in the result set. So it will only tell me the position, that the first record is satisfying the condition, 10th record is satisfying the condition, and so on. But it does not retrieve the records for me. So in order to retrieve such records, what we do is we create a B plus tree like index on the record numbers, and we feed in through the root the record numbers into this B plus tree, and then it takes us to the corresponding pointers that are there at the leaf levels. So if you want to retrieve the records, then you'll have to go to the take help of some conventional tree-based indexing structure. B plus tree is a good choice for this. And then we have what is called as a space requirement. So this also tells us something about the compactness of bitmap indexes. So you can see on the, let me clear the annotation first. Yeah. So unique column values. So this is basically the column cardinality, right? And cardinality in percent. So cardinality in percent means how many distinct values are there for the given with respect to the total values in the table. So here cardinality is 50%. Here it is 10%, here it is 1%, here it is 0.01%, and here it is less than 0.01% of the total number of records. So if I create a B tree index on this, so I would take 15.29 units, 15.21, 14, 13, 14, 13. So you can see that there is not much change as we, it is not dependent in some way on the cardinality. So it is kind of independent of the cardinality. Whereas if you look at the bitmap space, so here it is 12.35 and 5.25, 2.99, 0.38 and 0.78. So it goes down with increase with the cardinality. So as the cardinality goes down, the space requirement also goes down, and that is very clear to see that because we are creating a bit vector for every distinct value. So the more the distinct values, the more would be the space requirement. And bitmap indexes are good in the sense that for each bit in any bit vector, I need just one bit to store it. Okay, so we work with bit level operations which are supported by almost all programming languages. And then bitmap indexes for large data sets. So there are 2-3 things that we try to do. So we talk about compressing them, encoding and compression. So basically these are related things. Encoding may or may not lead to compression, right? So here we are trying to work on 3 things. So reduce the number of bitmaps or reduce the number of operations. So it does that. Compression reduces the size of each bitmap and may also speed up logical operations. So this will take up in the next lecture. And then there is binning. Binning is basically used to reduce the number of bitmap in bit vectors. Basically bitmap and bit vectors are used interchangeably. Right. So now so let me start with this with the binning first. So suppose there is an attribute NLB and it has values from 0 to 4000. So what we can do is, instead of creating a bitmap for each distinct value, we create a bitmap for a range of values like 0 to 200, 200 to 400, 400 to 600. Like this we'll have 20. Now suppose there are 4001 distinct values, say starting from 0 to 4000. So I would have to create 4001 bitmaps, right? And now instead of this, I am creating only 20 bitmaps because I am clubbing values or binning values from 0 to 200, then 200 to 400, and so on, and going up to 4000. So this helps in reducing the space requirement of bitmap indexes, and especially when you are dealing with the high cardinality attributes, when you are trying to create bitmaps on high cardinality attributes. So this is what is coming next. So bitmap indexes for high cardinality attributes. So as we know, bitmaps are well suited for low cardinality columns because the space requirement is very, very less, as we saw in that table also just a while ago. In a data warehouse environment, it may be required to use bitmap indexes for high cardinality attributes. So many attributes can be of high cardinality, and space requirements go up as we build a bitmap for a high cardinality attribute, because we have to create a bitmap for each distinct value of that attribute. So for example, in scientific databases, the cardinality of certain attributes can be very, very high. This should be high H. Okay, right? And in such situations, we use the technique called as binning. So binning reduces the number of bitmaps, as I showed you in the previous slide. So let us take an example. Before that, let me give you some more details about binning. Yeah, the example follows this. So the basic idea of binning is to build a bitmap for a bin rather than each distinct attribute value. So that helps me save space. One bitmap for each bin rather than for each distinct value. And this strategy dissociates the number of bitmaps from the attribute cardinality and allows one to build a bitmap index of a prescribed size irrespective of the attribute cardinality. So I can create my bins according to the space available to me, and I can handle high cardinality attributes very, very easily. But there are some kind of problems that are introduced because of this. So first and foremost problem is how to bin. Like, what should be the bin size or bin width, right? And and how many bins I should create. So all these are questions that come to our mind. And the second problem is that of candidate check. So I'll give you details of this. Now suppose these are the this is the record ID on the first column. Then these are the original values of this, right? Now what I'm doing is, you can see the values actually vary from 0 to 50 in this particular example. So we have created 5 bins: 1, 2, 3, third bin, fourth bin, and this is the fifth bin. So 0 to 10, 11 to 20, 21 to 30, 31 to 40, and 41 to 50. Now what we do is to create this bitmap. So the value is 5, so it comes under 0 to 10. So that's why we put a 1, right? And rest of the things are 0. Similarly 34, it comes under 31 to 40. Now 23 comes in this range, 21 to 30 in this bin. So that's why we put. So a value. So for creating this bit vector, what we need to do is look at each value, original value, and see in which bin it lies and put a 1 against that bin, right? So similarly, I have created this bin for all the for the remaining values. And now suppose I have a query A. This is the value for A attribute. So A is between 37 and 8. Okay, so now what I need to do, that I have to answer this query, right? I need to take 8 lies here and 37 lies here. So these two bins here and here, so wherever there is a 1 in these two bins, those would qualify for the answer or for the result, is it not? So these two are called as internal bins, and the dark gray ones that are there at the edge of the query, these are called as the edge bins. And edge bins create problems because I am looking for values greater than 8, right? Now values in this can be less than 8 as well, less than or equal to 8 also. Like you can see, this value is 5, which is less than equal to 8, 6 is less than equal to 8, and so these are two values that would create problems, because if I retrieve all the values from 0 to 10, not all of them would be greater than 8. So what I need to do is, I need to actually retrieve the value, right, from the database and check what value it is. And once I check, after checking, if it qualifies the condition, I put it in the result set, otherwise I discard this. But for checking, retrieving the values, you have to go to the database, right? So this would require IOs. So that is why working with edge bins is difficult, and this process of retrieving the records physically from the database and checking whether it qualifies for the result set or not is called as candidate checking. So any binning strategy should try to reduce or minimize the number of candidate check, or minimize candidate checking, or in other words it should try to minimize the number of edge bins that are there. So accordingly you decide on the bin boundaries. So given a query set, so you should look for bin boundaries in such a way that the number of edge bins are minimized, and once the edge bins are minimized, the number of candidate checks would also be minimized, because on the edge bins only we need to carry out the candidate checks. So binning bottleneck, so this is what I just explained to you, is candidate check problem. So candidate check problem, suppose you have an equality query, a is equal to 8 and there's a bin 0 to 10. Each tuple has a 1 for the bin is a candidate for the result set. So what I need to do is, and not every value that has a 1 would indicate that its value is 8. So what I need to do is I need to go to the database and retrieve all the records and see if it is 8, I put it in the result set. If it is not, I discard it. So expensive exercise as it involves disk IOs. So a good binning strategy would minimize the number of candidate checks. Equivalently, a good binning strategy will minimize the number of edge bins by suitably choosing the bin boundaries. And here I would like to refer to one of our papers. So one of the authors is me in this, and this work I did with one of my PhD students. So you can see this article. It was published in ACM Compute, and this talks about some strategies for binning. So that the candidate checks are minimized. So now with this I basically come to the end of this introduction to binning, introduction to bitmaps and the corresponding operations on them, and suitability or making them suitable for high cardinality attributes using strategies like binning. And there's another related topic which I feel is linked but not suitable for a first course. And since I have given you enough background on bitmap indexes, so you can look at bitmap join indexes, which facilitate join operations. And as you know, join operations are very critical to data warehousing. So it is basically like pre-computing the joins and the records that qualify. So I create a kind of a bitmap index which I pre-compute and keep for the join, which facilitates the join. So you can read about join indexes, and then join indexes are implemented as bitmap join indexes. So the two concepts are linked. So I would suggest that if you are interested, you can read through bitmap join indexes. And now with this I come to the end of this first lecture in this submodule, and the next topic is compression techniques for bitmap indexes. So I'll be talking about this in the next lecture. Thank you.